In this video, we'll be looking at characteristic IR absorptions. This schematic of an IR spectrum shows the different zones. So here we have the YH zone, here's where we have triple bond absorptions, here's where we have double bond absorptions, and then down here is where we have single bond absorptions. And although there exist tables of IR data, I like to compile our own set of important IR values. If we start out thinking about alkanes, we know that we're going to have some sp3 hybridized carbons connected to hydrogens. And these are going to absorb around 2,800 to 3,000 inverse centimeters. We also have carbon-carbon single bonds, where these would be sp3 hybridized, and these are usually not easily identified. In an alkene, we're going to have sp2 hybridized carbons connected to hydrogens, and these usually show up around 3,000 to 3,100 inverse centimeters. And we will also have a carbon-carbon double bond that will absorb around 1650. For an alkyne, if it's a terminal alkyne, we will have a carbon that's sp hybridized connected to a hydrogen. So this CH bond absorbs around 3,300 inverse centimeters, and the carbon-carbon triple bond absorbs around 2,200. Another type of hydrocarbon would be an aromatic ring, and these carbons are sp2 hybridized, and so they will also absorb in the 3,000 to 3,100 range. So I'm just going to add that here, and I'm writing ARH, where AR stands for an aromatic, not for argon. But what's different between alkenes and aromatics is that the aromatic carbon-carbon bond, this has two absorptions, usually around 1,500 and 1,600. Now keep in mind with aromatics, all we know about aromatics so far is that they would look like benzene or have benzene with some substitutions on it or something like that. And it's drawn as double bond, single bond, double bond, single bond. But notice this doesn't behave the same way as carbon-carbon double bonds. So we can actually look at this as some evidence for resonance, because the aromatic carbon-carbon bond is not the same as a carbon-carbon double bond or as a carbon-carbon single bond, but it is something distinct. Another really important bond type that falls into this zone here is the carbonyl. And carbonyls absorb around 1,700 inverse centimeters. Now the range is going to go maybe as low as like 1670, and it could be as high as 1800, but that's getting into carbonyls that are in anhydrides or other types of compounds that we're probably not going to look at too much in this class. And some books will focus on the fact that if your carbonyl is part of an aldehyde or a ketone or an ester or an acid, it will have slightly different absorptions. And so in many cases, they will give tables that say this carbonyl is one thing and this carbonyl is another thing and this carbonyl is something else. But I'm more concerned about the overlap. So I don't think it's very easy to use the exact carbonyl absorption frequency and use that to figure out what type of compound it is. So instead, what I recommend is that you identify your carbonyl, and then you look for evidence elsewhere to figure out whether that carbonyl is part of an aldehyde or part of an acid or part of an ester. So speaking of carbonyl containing compounds, one important one is an aldehyde. And when we have an aldehyde CH, so what I'm talking about is the carbonyl CH, this tends to have two peaks at about 2750 and 2850. Now, this carbon is sp2 hybridized, but it doesn't absorb the same as alkenes or aromatics. So this one is something unique. Now we have to be careful because 2850, this falls into the range of a regular CsP3H. So just having a peak at 2850, that might be one of these. But if you have a carbonyl, and if you have a peak at 2750-ish as well as 2850-ish, then that is very strong evidence for an aldehyde. Moving on to other functional groups. If we have an alcohol, OH, these tend to absorb around 3,300 inverse centimeters. They tend to be a little bit broad. And if we have an acid, OH, these tend to absorb around 2,500 to 3,500. Now, this is not a range that sometimes it shows up at 2,800, sometimes 3,200. The acid OH is a really, really broad peak. And so it tends to stretch out all the way from about 2,500 to 3,500. It's really a unique looking peak on the IR spectrum. And if we have an NH, these will also absorb around 3,300 inverse centimeters. For the most part, we don't have to worry about single bonds, but there are a few peaks that tend to jump out of the fingerprint region, and one of these would be a CO single bond. Depending on whether that carbon is sp2 or sp3 hybridized, this could be anywhere from about 1,000 to 1,200 inverse centimeters. So this one, it just appears in a broad range. It's not a broad peak. So these values, I think, are the most important ones to be on the lookout for. When you're looking at an IR spectrum, keep in mind that you want to focus on 1500. This will be one of the magic numbers because above 1500 is the diagnostic region and we need to focus there. Below 1500 is the fingerprint region and we need to glance there. Another magic number is 1700 because this is where carbonyls absorb. And these tend to be very strong signals, so they're really noticeable. And then the third magic number that I want you to focus on is 3000, because this is where we have the division between sp3ch and sp2ch. So just below 3000, this is where we're going to have our sp3ch, and just above sp2ch. And as I mentioned before, although I don't need you to memorize all of these numbers, I do expect you to get to know all of these numbers. Not necessarily the ones that are not here but are included on other IR tables. Focus on these and you're going to be able to interpret a lot of IR spectra. Now let's look at the spectrum in a slightly different way. If we focus on 3000, so around here is where we're going to have our sp3ch. Here is our sp2ch, and around here would be our spch, and then about here and here is where we would have our aldehyde CH. Our amine NH is going to show up around here. Our alcohol OH is also going to show up around here. So specifically an alcohol OH, and an acid OH is going to show up all the way around here. Around here is where we find carbon-carbon triple bonds. And in comparison, this is where we find carbon-carbon double bonds. And then about here and here is where we see our aromatic carbon-carbon bonds. And then somewhere in here is where we have our carbon-carbon single bonds. Here is where we find our carbonyls. So, oops, the way I've drawn it, it looks like it overlaps with the carbon-carbon double bond. Not really. These tend to be just a little bit lower, and so these are closer to 1650, whereas these are going to be closer to 1700. And we might also have carbon-oxygen single bond around here as well. So it looks like we have some issues with multiple signals that appear in the same region. So how can we tell which is which? Well, there are other characteristics of the peaks that we still need to talk about. So this gives you another way to think about the location of different peaks in the IR spectrum. Now, please note that all of these are stretch vibrations. So we're talking about the stretching vibrations, either symmetric or antisymmetric. And usually it's the stretching vibrations that are the useful ones. Many of the bending vibrations get lost in the fingerprint region, and so they're not very useful. But there are, of course, some exceptions. Now, for some compounds, such as alkenes or aromatics, we can actually get some really useful information from a bend. And so this is the OOP region, which is out of plane bending. So the out of plane bending region. And there are tables of data that have been collected. And what we see is that between about 700 to 900 or 700 up to 1,000, you tend to get the out of plane bending peaks that differ significantly depending on the substitution of your alkene. So if we have 3 hydrogens and only 1 alkyl group, then we tend to get 2 strong signals. If we have 2 substituents on one alkene carbon and 2 hydrogens on the other alkene carbon, we tend to get 1 signal a little bit below 900. And so looking at these details can often give you useful information. In general, we're not going to have to interpret these, but I want you to be aware that this information exists. So if you're working on a really challenging IR, maybe this is something that you're doing in lab, just know that there is more information available that you can use. I also just wanted to point out the aromatics. So actually from closer to 600 up to 900, we have a variety of patterns depending on whether it's monosubstituted, whether the substituents are next to each other, further removed, across from each other, etc. We have different substitution patterns, and they all give pretty unique and identifiable patterns of IR absorptions. Then in addition to these that can be used to figure out exactly what your substitution pattern is, there's also an overtone region. And this goes from, it's like 1666 up to about 2000. And this is another area that gives a very particular pattern of peaks. And it kind of looks like 4 fingers pointing down, or only 2 fingers, or the first 2 fingers. It gives very unique patterns, which again, you can interpret a little bit more deeply to get more information. But in general, as we're working on spectra in class, we're not going to have to worry about these. On these next several slides, we're going to look at some sample spectra and try to focus on different regions or on different types of bonds. So here, we're starting by focusing on CH. So here we have sp3 hybridized CH. In this one, we have sp3 hybridized CH and sp2 hybridized CH. In this one, we have sp3 hybridized CH as well as spCH. And finally, in this one, we have some sp3 hybridized CH. And for this one, it'd be good to get a ruler and double check, but this is around 2750, this is around 2850, so these are the peaks for our aldehyde CH. So keep in mind, you might have multiple types of CH bonds in your molecule. Make sure that you distinguish them and make sure that you identify all of them. You don't want to glance at this and say sp3CH. You want to look at the detail. And so these would be probably your sp3CH, and these would be your aldehyde CH. Here we're focusing on carbon-carbon bonds. Our first spectrum is an alkane, and our alkane carbon-carbon bond doesn't give us anything useful. In this spectrum, notice we have our sp3CH, and then this would be an sp2CH. So let's keep looking for some sp2 hybridized carbons, and what we have here is a signal at 1650 for the alkene carbons. Here we have a significant peak around 2100, 2200, and that goes along with the SPCH that we have. So here is our carbon-carbon triple bond. And it really stands out nicely because there's no other absorptions in this area, so it's nice that a triple bond is really going to stand out. Now finally, looking at this spectrum, we have sp3CH and we have several sp2CH, and we don't have a peak at 1650. Instead, we have a peak at 1500 and 1600. So this corresponds to an aromatic compound. Now, as I just mentioned about the OOP bending, here in the fingerprint region, we do have some peaks here. This one got cut off, but this would be one of those OOP bending that gives us useful information when it's actually there. And then this is that overtone region. Sometimes it's clear, sometimes it's not, but it just gives a very particular pattern. So that's just kind of another cool thing when you can actually see it. On this slide, let's focus on our carbonyl. So the carbonyl around 1700, this is really strong. And so this one is the strongest out of all the peaks. And that's going to be a common thing you're going to see, is that the carbonyl should really just jump out at you. Now, these are all different types of carbonyl containing compounds. And if we look at where the carbonyl shows up, this is a little bit above 1700. This is a little bit more above 1700. This one is almost the same as this one. And this one is pretty much right on 1700. So just looking at the exact value, I wouldn't really want to use that to figure out what type of compound it is. I would rather look for other evidence. So we see this, we know it's a carbonyl, and there's nothing else that really jumps out at us. So this one is probably a ketone. Looking at the next one, here is our carbonyl, and notice here we have our aldehyde CH, so we know that this one corresponds to an aldehyde. Here's our carbonyl, and in this one, we also have this really strong peak. It's right around 1200. This would be a C single bond O, and assuming that this C double bond O and this CO are connected to each other, then this is probably an ester. And in the last one, we have our C double bond O. This one might be a C single bond O. It's not as strong as what we saw here, so I think I would call that a C single bond O with a question mark. But notice what we have here, this huge peak. This is an acid OH. So we know that this compound must be a carboxylic acid. So we don't have to worry about over-interpreting exactly where the carbonyl is, as long as we can look for other evidence to figure out what type of compound we actually have. Next, let's take a look at OH and NH. So NH and alcohol OH both absorb around 3300, the acid OH 2500 all the way up to 3500. So here we have an alcohol OH. And this is another signal that tends to be really strong, and it's a lot more broad than some of the other peaks that we normally see. So this is a distinguishing feature of an alcohol OH. Here we have our carboxylic acid OH. So way more broad and also messy. Where this one is nice and smooth, this one has a little more jaggedness to it. So alcohol OH compared to acid OH. Now over here we have an NH, and these are also a little bit broadened, but not nearly as strong as an alcohol OH. So although just looking at the numbers, you might be concerned about, well, how can I tell them apart? It's really quite easy to be able to tell them apart. Now, the amines can differ whether the nitrogen is connected to two hydrogens. You're going to get either 2 or 3 peaks in this area. If the nitrogen is connected to one hydrogen, then you get 1 peak in this area. If the nitrogen is connected to no hydrogens, which means it's connected to 3 carbons, well, then we don't get a peak here because this is the NH region, and if there's no NHs, there's no signal. So just looking at the number where something absorbs is only giving you part of the picture. Thinking about the characteristics in terms of how broad, how strong, these are other really important characteristics too. And finally, if we focus on 3300, so here we have several types of bonds that all absorb around 3300. If we're just looking at the numbers, it's difficult to tell them apart, but we have to focus on the strength and the sharpness or lack thereof of the signal as well. So this one is an SPCH. And so this tends to be pretty strong. Sometimes they're not quite as strong as this one is, but pretty strong, but they're quite sharp. This is an alcohol OH, very strong, and it tends to be broad. So you're not going to mix up an alkyne CH with an alcohol OH. And then here we have our NH2 or NH, and clearly distinguishable from an alcohol and clearly distinguishable from the SPCH as well.